Hi guys, thanks for watching this video. The paper I'm presenting today is called Sieve Estimation of Time-Varying Factor Loadings. Although the title specifies the estimation of factor loadings, this paper has in fact accomplished a little more. This is a standard static factor model. We observe a large panel of data xit, and we model them as a linear combination of a relatively small number of common unobserved factors, ft. And lambda I are the respective factor loadings. This model has been very popular in the past 2 decades due to its simplicity, the good performance of its estimators, especially the principal component estimator, and most importantly, its ability to model big data. In this paper, I'm going to make a very small change to this model. I will allow the factor loadings to be time varying. However, this small change has a big impact. In a standard factor model, we observe n times t data points, and we would like to estimate t times k parameters in ft and n times k parameters in lambda. So we still have a lot of data points for each parameter. While in this time-varying factor model, we still only observe n times t data points, but we want to estimate n times t times k parameters in the varying loadings. So we have turned the blessing of dimensionality into a curse. And obviously, we have to impose some restrictions on the factor loadings. In the literature, there are several ways to do so. In a 2013 Journal of Econometrics paper, Bates and co-author find the principal component estimator can consistently estimate the factor space under either of the following conditions. First, if lambda is a white noise process, and second, if lambda is a random walk process scaled by a factor of h, which is small o 1 over root t. We know that a random walk process grows at the rate of root t. This second condition essentially means that the time variations of the factor loadings have to be negligible asymptotically. This seems to be a little too restrictive for a time-varying factor model. Besides, the estimation of the factor loadings is not considered, since its time variation is treated as an error term. In a more recent paper, Su and Wang assumed that the factor loadings are some smooth functions of time. They propose a kernel-type local principal component analysis and find that it is consistent for ht up to a rotation matrix ht. It should be noted that it is common in factor analysis that the latent factors and the factor loadings are not separately identifiable. The reason is that we can always multiply some matrix to ft and its inverse to lambda and obtain observationally identical xit. However, this problem is much more crucial in our setting. Although we have a consistent estimator for each t, we still cannot obtain the factor space. So the literature has left some problems unsolved, and they have motivated the present paper. In this paper, we try to answer the following questions. First, given that there are some non-trivial variations in the factor loadings, can we estimate the latent factors with the rotation? This problem has been solved in the context of a standard factor model, and we will show that the solution can still apply when the loadings are time varying. Given an estimate of the latent factors, this model becomes a varying coefficient regression model. So the second question is whether we can estimate the time path of the loadings. For this purpose, I will propose a Sieve estimator and show that it is consistent with mean square. Now, since I have to employ some non-parametric methods for estimation, some efficiency is lost. So the next question is, if some factor loadings are in fact constant, can we estimate them parametrically and more efficiently? In practice, usually it is unknown whether the loadings are constant or not. So can we identify them? And we will go through these questions one by one now. This is the roadmap of the remaining parts of today's presentation. I will first briefly talk about the model, and then I will discuss the estimation procedures and the asymptotic results. Finally, I will also show you some simulation results. So this is the time-varying factor model. I will assume that the latent factors are weakly stationary and the idiosyncratic errors are only weakly autocorrelated. The most important part of this model is the varying loadings. I will assume them to be some Hölder continuous functions of time. So this has already included a very large set of functions. For example, all smooth functions are Hölder continuous with exponent 1, and all fractional Brownian motions with Hurst coefficient h are also Hölder continuous with alpha smaller than h. Now we consider the estimation of this model. Since we have assumed lambda to be Hölder continuous, if we only consider for some t that is close to s, the difference between lambda it and lambda is small. In fact, as capital T tends to infinity, this difference converges to 0. Therefore, we can treat it as an additional error term, and in fact this holds true for all t that is not too far away from s, and we can treat this subsample as generated by a standard constant loading factor model. With this in mind, I propose to split the sample into n equal parts, and for each subsample, we compute the principal component estimator. I will call this the rolling PCA because it is nothing but the standard principal component estimator in a rolling window basis. And here is our first result. We can show that for each subsample, the principal component estimator can consistently estimate the factor space of the respective time period. The estimation errors can be separated into two parts. The first part is standard for the principal component estimator. Note now that sample size is n times tau for each subsample. The second part resembles the approximation errors. It appears because we ignore the time variations in lambda and treat it as a constant. Apparently, this result is not good enough since we still have this k times k rotation matrix H. So for each subsample, we have to impose k times k restrictions to pin down H. Following the literature, there are several identification schemes. Here, PC1 is implicitly assumed in PCA, except that we have to restrict the diagonal elements of lambda prime lambda to be distinct. PC2 is a structural restriction. We assume that the first series is affected by the first factor only, and the second series is affected by the first two factors only, and so on and so forth. Finally, in PC3, we assume that we have a proxy for each factor. And after choosing an identification scheme, we can apply the transformation to the PCA estimators accordingly such that the restrictions are satisfied. When it is done, we can show that for each t, the transformed estimators are consistent, and more importantly, with their rotations. And we can finally get rid of the H matrix. Now that we have answered the first question, we can move on and focus on the estimation of factor loadings. As I've said, given the latent factors, the time-varying factor model is essentially a varying coefficient model. So to turn it into a constant coefficient one so that we can carry our estimation by standard approach, I propose to approximate the loadings by the so-called B-splines. If we can also represent the varying loadings as a linear combination of the B-splines, then we can augment the common factors by the B-splines, and the model becomes linear to the canonical products of the factors and the B-splines. And given a consistent estimator of the latent factors, it is just a simple linear regression problem. And before we move on, I would like to make a little digression and talk a little more about the B-splines. B-splines are also called basis splines, since any spline functions of a particular degree can be represented as a linear combination of B-splines of that degree. B-splines are completely defined by the knot sequence and degree or order. And for simplicity, I will only focus on B-splines with equidistant knot sequence that divide the sample into n pieces. This graph shows the spline basis with 3 interior knots. And this is what happens when the number of knots increases. We can observe that the span of each spline function becomes smaller. And this is in spirit very similar to a kernel-type estimator. Since we assume that the lambda is Hölder continuous and has modulus of continuity alpha, theorems in spline approximation tell us that there exists coefficient c such that the approximation error of the spline function converge uniformly at the rate of n to the power of alpha. Now, substituting this to our model, we can transform it to a model with constant coefficient. And now this model can be estimated simply by OLS, and the lambdas can be reconstructed accordingly. And here comes our main result. We can show that this estimator is consistent in mean square, and it even converges uniformly if the modulus of continuity is larger than 1/2. One of the advantages of this spline estimator over a kernel estimator is that it can be easily modified to take into consideration of the presence of constant loadings. So this allows us to answer the third and fourth questions raised at the very beginning. Now suppose that some fact loadings are constant, then we have a partially linear model. There are some factors f1 that have varying loadings and some other factors f2 that have constant loadings. It should be noted that for different i's, the compositions of f1 and f2 can be different. Following exactly the same procedures, we can approximate the varying loadings by B-splines and transform the model into a simple regression model. And we can now obtain the estimated coefficients by OLS. It is exactly the same as the Sieve estimator I proposed just now, except that we only need to omit f1 but not f2 in this case. And the knowledge of constancy of factor loadings can be very easily incorporated in this estimator. And we can show that the estimator for the parametric part is consistent in a pointwise sense. Unfortunately, we cannot obtain a better convergence rate because it inherits the errors in the step of rolling PCA. But simulations show that the estimation of the parametric part is in fact very accurate. In practice, of course, we usually do not know whether the loadings are constant or not. The last part of this paper develops a very simple way to determine it. We consider for each cross-sectional unit and for each factor and check whether that particular factor loading is time-varying or constant. To do so, we compare two criteria functions TVC1 and TVC2. TVC1 consists of the square sum of errors computed under the assumption that all loadings are time-varying. The estimated loadings used are consistent no matter whether lambda ik is constant or not. And TVC2 is computed under the assumption that lambda ik is constant, and so it is consistent only under model 2. As a result, if model 1 is the true model, TVC2 will be larger than TVC1 since it is not consistent. And if model 2 is true, the two sum of square terms will converge to each other. So we need GT to be set as a large number to ensure that TVC1 is larger than TVC2 in this case. And this theorem states what we need and what we have. We have to set GT such that it converges to 0 as t tends to infinity. but it converges slower than either n to the power of alpha or cn tau. Now, since alpha is unknown and can range between 0 and 1, we propose to set gt as 1 over log t such that these two criteria are always met. Finally, let's take a brief look at some simulation results. We generate a two-factor model in which one factor has time-varying loadings and the other has constant loadings. The idiosyncratic terms are IID, and the latent factors are two independent AR1 processes. In this study, we will employ PC2 for identification purpose. In this table, we first take a look at the estimation results of the latent factors. Here, the R-squares are the average R-square coefficient of regressing each true factor on the respective estimated factor. We can see that they are all over 95%, and it shows that our rolling PCA and the identification transformation can accurately estimate each factor, even when the factor loadings have non-trivial time variations. In this second table, we show the estimation results of the factor loadings. We first take a look at the mean square errors of gamma, the estimation of the constant loadings. It is less than 0.01 in most settings and is much smaller than the MSE of the varying part. This suggests that even though theorem said it inherits the estimation error of the first stage estimation, it is in fact very accurate. So in practice, it is highly recommended to identify the constant loadings first for an improved estimator. And now return to the MSE of lambdas. First, we see that it drops when t increases, as theorem indicates. Besides, it is also clear that the MSEs are large when h is small. The reason for this can be clearly shown in the following graphs. In this graph, we plot the true factor loading process with the red line. It is a fractional Brownian motion with Hölder coefficient 0.3. We also plot the average estimated path with the dotted line and the error bounds with the gray shade area. We can see that the loading process is very noisy, and the spline approximation can only capture the large movements, but not the local variations. When h becomes larger, the loading paths are smoother, and the approximation works better. Finally, in this table, we show the performance of the test of loading constancy. Here, Pm1m1 is the empirical probability that our test indicates a varying loading when the loading is truly varying, and similarly for Pm2m2. Our test can correctly distinguish around 95% of the time for a moderate t, and when t is large, the probability of success is close to 1. This shows great support to our method. To conclude, this paper considers a time-varying factor model and provides answers for these 4 questions. First, we show that the rolling PCA, together with the identification schemes proposed in the literature, can consistently estimate each latent factor with the rotation, even when the loadings are time-varying. Second, we approximate the loadings with B-splines and propose a Sieve estimator. We show that the estimated time path of the loadings are consistent in mean squares. This estimator can be modified to accommodate constant loadings, and the estimator of the parametric part is consistent in a pointwise sense. Finally, we also develop a simple model selection approach for testing the constancy of the loadings, and simulations show good performance of our test. That's the end of the presentation. Thanks for listening, and all comments are welcomed. Thanks.